Hey guys, Professor Sweeting here. In this video, we're going to wrap up our discussion of coloring problems with the face coloring problem. We're going to cover its definition, some of its very direct applications, and a general algorithm for finding a minimum coloring of a graph. And this is going to be regardless of the specific component. So this algorithm will help us find face colorings, vertex colorings, and edge colorings. Alright, so to begin discussing the face coloring problem, a definition of what a face is within a graph needs to be established. The concept of a face, as we'll define it, will only make sense for a special family of graphs known as planar graphs. These are graphs which can be drawn on a sheet of paper, that is to say a plane without any of their edges crossing. So let's look at some examples. So I've gone ahead and drawn three graphs here, right? So we can see the first graph, which has this is the first graph, which has 3 vertices, 3 edges. Second graph has 4 vertices, 5 edges, and then the last is the complete graph on 5 vertices, which has 5 vertices and let's see, 5 times 4 divided by 2, 10 edges. Okay. All right. So this is graph 3. So the first graph is clearly planar. So if we can draw a graph, right, on a sheet of paper, with its edges and its vertices, right, and none of the edges cross, we can definitively conclude, right, that it is a planar graph. That is, by definition, what a planar graph is, right? If we can draw it like that, with no edges crossing, that means it's planar. All right, so we can clearly see that this is a planar graph, right? None of the edges are crossed, okay? We can see that 2 is also a planar graph, okay? Right? 3, it's not immediately clear whether or not it's a planar graph, but we'll see that it's not a planar graph. I mean, we can immediately see that this representation of the graph wouldn't indicate that it's a planar graph, right? So a graph can be drawn in multiple ways, as we've seen, right? So, we can draw the complete graph on 5 vertices like this, right? Which we've discussed in class, where you kind of, when you're drawing a complete graph, have all of the vertices along a circle, and then connect them on the outside, and then just connect them on the inside. So you get something that looks like this, right? Or you can just, kind of scatter the 5 vertices, and then just kind of, connect them however you'd like, so long as they're all connected to one another directly via an edge. So that's perhaps another representation. All right. And this representation, right, it represents the same graph. Okay, so from the graph theoretical viewpoint, 2 collections of edges and vertices are the same if you can, I don't want to get too technical because this is beyond the scope of the class, but 2 graphs are the same if you can find a 1-to-1 correspondence between their vertices. So if they have the same number of vertices, and you can find a labeling of both vertices, right, in each of the vertices in both graphs, such that the edges will connect, of each graph will connect the same vertices. All right, so I don't want to elaborate on that, but that just means that a graph can be drawn multiple ways, and these ways are equivalent from a graph theoretical standpoint if you can kind of match up the vertices to one another so that the edge relationships are the same, right? So, as we'll see, regardless of the representation of this graph, so if we redraw this graph in equivalent ways, like so, right? No matter how we redraw it, it's always going to be non-planar, right? And we'll talk about that more later, right? But an example of the representation mattering for concluding whether or not, being able to conclude whether or not a graph is planar, we can look at something as simple as the complete graph on 4 vertices, right? All right, so this is the, let's see, is this a complete graph on 4 vertices? 3? Yeah, so this is the complete graph on 4 vertices, right? Every vertex is connected to every other vertex via an edge directly, okay? Right, let's give some kind of labeling to the vertices here. Okay, we can't conclude that this graph, this complete graph on 4 vertices, is planar, right? Because in the way we've drawn it, we have edge crossings. So 2 edges cross right here, okay? But I can redraw this like so. Oop. Ah, yes, okay. And keep this edge. Alright, so I can redraw it like so. Okay, and in this case we have no edge crossings. Okay, every vertex is connected to every other vertex via an edge directly, but we have no edge crossings in this diagram here. And I hope you can see that these two graphs are kind of equivalent in that we have the same number of vertices, and in each labeling, every vertex is connected to all other vertices. So they're the same graph from a graph theory standpoint. Okay, so this graph, we can then conclude this complete graph on 4 vertices is planar because we found one such representation, one such drawing in which the edges of that representation don't cross. Okay, all right. Alright, so again, planar graphs are just graphs which can be drawn without any of their edges crossing. So these graphs, planar graphs, will split the plane to which they belong, right? That is to say, the surface on which they're drawn, into distinct regions separated by the edges of the graph. So let's see that. Okay, so for this first graph, which we said was planar, right? We can see how this kind of splits the plane, or the page on which it's drawn, into 2 regions. There's the region on the inside, which is bounded by the edges, and then there's everything to the outside of the graph. Okay, so for the second graph, we can see how it splits the plane, or the page on which it's drawn, into 3 regions. We have the region bounded by ACB, A, like these 3 edges, right? And then CDBA, right? So these 3 edges that comprise that path, right? And then everything to the outside. So this, we have 2 regions here, 1, 2, everything on the inside, everything on the outside. We have 3 regions here, 1, 2, 3, okay? And then for the complete graph on 4 vertices, this splits the plane into 4 regions, right? 1, 2, 3, 4, okay? So these, again, these planar graphs will split the plane on which they're drawn, the page on which they're drawn, into distinct regions, and we call these regions faces. All right, so the reason why we only define this notion for the restricted class of graphs, right, so planar graphs, is because for planar graphs, no matter how you draw them, they'll always have the same number of regions with the same positional relationship. Okay? So for example, if we have this graph right here, okay? This is a planar graph. We can redraw this graph maybe by moving the edge from the inside onto the outside. Okay, let's do that. So this is the same graph, same kind of number of vertices and edge relationships between those vertices, and it still, this other representation will split the graph into 2 adjacent regions and then a 3rd region on the outside. Okay, so this property is only well defined when you can draw the graph in this way, right? So for such a graph, there's no equivalent way of making sense of regions on the inside, because these, if you were to try and go by these edge crossings as regions, you'd find that in different representations, you'll have inconsistent behavior, right? You won't have the same maybe number of regions or the same kind of positional relationship between those regions, right, as you would in the case of planar graphs, okay? So, all right, so that's why we only talk about the concept of faces, which are regions bounded by edges of the planar graph, or edges of a graph, in the case when the graph is planar. Okay, so the face coloring problem is the minimum coloring problem with respect to these faces of planar graphs. That is to say, we are interested in finding the minimum number of colors/labels required to assign one to each face of a planar graph so that no 2 adjacent faces share the same color. 2 faces are considered adjacent if their boundaries, which are composed of the edges of the graph, share at least 1 edge. So this minimum number of colors for a graph is known as its face chromatic number. So let's look at those examples, right? Okay. So in these examples, right? So in this first example, these two, right, faces. So the face that's bounded by everything, or these three edges on the inside, A to C, that edge, C to B, that edge, and B to A, that edge. So this face is adjacent to the face that is to the outside of those three edges, right? To the outside of the graph. Okay? In the second graph here, we have faces 1 and 2 are adjacent because they share an edge. And they both are adjacent to face 3. Okay? Alright, so all three of these faces, which are, with respect to this graph, this planar graph, are adjacent because they each share an edge. So this face shares an edge with this face, so they're adjacent. And then these two faces share an edge with the face that consists of everything outside of the graph. Okay. And then in the case of the complete graph on 4 vertices, which creates, which splits the plane into 4 faces, right? Which has 4 faces, right? The face bounded by AB, DA, AC, DA, CB, AC, right? And then everything to the outside. All of those faces are adjacent, right? So ABDA, so the face bounded by those edges, or the edges along that path, shares the edge AD with the face. You know, I hope you can see this, all right? And then both of these faces share edges with this face, and then everything shares an edge with the outside face, right? Which is not always the case. So let's look at an example of a graph where we have non-adjacent edges. So in each of these graphs, these planar graphs, or excuse me, in which we have non-adjacent faces. So in each of these, for each of these planar graphs, every face was adjacent. But for a graph such as this, maybe this is a rectangular network, if you guys recall, okay, where we have this kind of grid of vertices and edges. So we just had one with 9 vertices here. Okay, right? So this splits, this is a planar graph because it was drawn such that no edges are crossing, right? So it splits the plane into a number of regions, which we call faces, right? So everything within this region bounded by those 4 vertices here, everything bounded by these 4, those 4, this 4, and then everything to the outside, right? So in this situation, okay, faces 2 and 3 are non-adjacent because they do not share an edge with one another. And faces 1 and 4 are not adjacent because they also do not share an edge with one another. So this is an example of a planar graph with non-adjacent faces, right? But again, every face, right, on the inside here of the graph, 1, 2, 3, and 4, is adjacent to the outside face. That also may not always hold. So let's look at an example of that situation, right? So here's a planar graph. All right. Okay, so, all right, so this is a planar graph. Let's give these edges some vertices some labels here. Okay, it's a planar graph because we were able to draw it without any of the edges crossing. Okay, and let's maybe add an edge here, here, and here. Okay, still planar, none of the edges cross. All right, and so this planar graph splits the plane into a number of distinct regions bounded by its edges, right? So this region bounded by the edges AB, BD, DE, and then EA. This region, and then this region on the inside, and then lastly this region on the outside, right? So all 3 of these regions are adjacent to one another, and each of these regions is also adjacent to the region on the inside, but this region on the inside, this face, so by the region we also mean face. So these regions are what we call faces. So this face on the inside, labeled by 4, is not adjacent to the face that consists of everything to the outside of the plane, right? So it doesn't always have to be the case that a face is adjacent to that, that every face of the graph is going to be adjacent to the face formed by everything outside of that graph. So this is a prime example of that. Okay, so anyway, again, the face coloring problem is the minimum coloring problem with respect to these faces. So we want to know the least number of colors required to assign one to every face of the planar graph, right? Such that adjacent faces have different colors, right? And we call that number for a graph, the minimum number of colors for a graph, the face chromatic number, all right? So what would be the face chromatic number of this graph? Well, let's redraw this. So we're going to actually look at that specific value for certain types of graphs. All right. Well, we're going to need different colors for each of these 4 graphs, or each of these 4 faces. Okay. Let's add these labels back. EF. Okay, so I have to, I'm going to be using labels for the colors because I don't have my markers at hand. Okay, so we can give this face, say, a label 1. This face needs to have a separate label, right? 2. This face needs to have a separate label 3, right? Because they're all adjacent. Okay, and then this face on the outside needs to have a separate label from those 3 because it's adjacent to each of these, right? But we can reuse that label for the inside face, okay? All right, so the face chromatic number of this graph is 4, right? We were able to make do, or we had to use at least 4 colors to assign one to each face so that adjacent faces have different colors, right? So because we had 4 faces adjacent simultaneously, 1, 2, 3, and the face consisting of everything to the outside, we needed to use at least 4 colors to color everything, right? So this face on the inside was able to have the same colors, the face consisting of everything outside of the graph, because they're not adjacent, all right? So we had looked at another graph earlier. Okay, this right here. So the face coloring number, or the face chromatic number of this graph is 2, right? So we'd color the inside something, or give it a label, right? This face on the inside, and then we'd have to give the face on the outside a separate label, right? So we were able to color every face of this graph, this planar graph, with only 2 colors, right? So that has face chromatic number of 2. And this has a face chromatic number of 4. All right. So we can look here. Again, for the case of this graph, we have this is the complete graph on 4 vertices. Planar graph separates the plane into 4 different regions, also known as faces. Right. They're each adjacent simultaneously, so we'll require at least 4 colors to color every face so that no adjacent faces have the same color. So this has face chromatic number of 4. This has face chromatic number of 3 because each of its 3 faces is simultaneously adjacent. All right. Okay. And then this has face chromatic number of 3. Okay. So, or actually 4, excuse me. Okay. Or actually, let's find out. Okay, so this can be colored something, right? Or given some label. We'll go by labels. This is adjacent, so it has to be given a different label, right? The outside is adjacent, so it has to be given a different label to both of these, right? So the outside, so we have 3 faces being adjacent simultaneously, so they each require different labels or colors. I don't have colors, so I'm using labels, right? But this is not adjacent to one of the three faces that we've already colored. So we can reuse the color of that face it's not adjacent to. And same goes for this, right? So we've colored every face of this rectangular network, this graph, with only three labels, right? Or three colors. So if these labels, remember colors, labels are interchangeable as part of this problem. So it's a labeling problem, these coloring problems, where the colors are the labels. Right, so this has face chromatic number of 3. So face chromatic number of 3. Okay, so those were summing. Oh, this was off the page. Okay, so again, we were coloring. We had to color these faces or give these faces different labels because they are all simultaneously adjacent to one another, right? And then we tried to reuse colors, which we could, because this face is not adjacent to one of those three faces, so we could reuse that color or label for that face. And then this face is not adjacent to, one of these four faces, so we're able to give it or reuse for it one of these, one of the labels for those faces, and therefore we successfully did the labeling with just 3 colors. So this graph has a face chromatic number of 3. So now, most of the graph families we looked at, those which had known solution to the vertex and edge coloring problems, do not belong to the family of planar graphs. This includes complete graphs with 5 or more vertices, and bipartite graphs with 3 or more vertices in each column. So remember, bipartite graphs were just formed by columns of vertices, right? 2 columns of vertices, one left column, one right column, and the edges in the graph were just those that connected every vertex in the left column to the vertices in the right column. So, for example, this is a bipartite graph. Yeah. Okay. All right. So now, So those bipartite graphs with 3 or more vertices in each of these columns are not planar, right? So we're not going to prove this, but that's just something that you should be aware of. In fact, a necessary and sufficient condition for a simple graph to be planar is for it to not contain as a subgraph the complete graph with 5 vertices or the bipartite graph with 3 vertices in each column. So not only, well, I guess this is a characterization of planar graphs, is that they don't contain, that's pretty poorly drawn, but they don't contain either one of these graphs as a subgraph. So every complete graph with 5 or more vertices will have this graph somewhere inside it, and every bipartite graph with 3 or more vertices in each column will have this graph, right, this bipartite graph with 3 vertices in each column as a subgraph inside of it. Okay, so every such graph, so most of the graphs, complete graph family, and most of the bipartite graph family, they're not planar graphs. So we can't talk about the face coloring problems for these graphs. However, we can still consider other families like cyclic graphs, rectangular networks, wheel graphs, and trees, which are all planar and have known solutions to the face coloring problem. Alright, so let's see that. Okay, so let's start with trees. Right, so recall that trees were graphs that were connected and had no closed off little tors, right? So this is a tree, whereas if we added this edge between these 2 vertices, it would no longer be a tree, okay? So we've looked at these extensively in this class, right? So these trees, right, graphs in this family, which are planar, have very easy solutions to the face coloring problem. Their minimum, or their face chromatic number is 1 because they don't close off any region. They don't close off any faces. So the only face that these planar graphs define is everything, like the entire plane. They're not kind of cutting off the plane into regions bounded by their edges, because that would violate their definition. Like they're, by definition, graphs that don't kind of separate the plane into different faces or different regions. Therefore, there's only one such region associated with the graphs in this family, and therefore we only need one color, right, for that one face. right? So that this one color or label for this one face, which is everything outside of the graph. All right, so the face chromatic number for trees is 1, always. Okay? All right, and then another graph family for which the face chromatic number is pretty easy to compute are cyclic graphs. So we talked about these before in both the vertex and edge coloring videos that we did. All right, so cyclic graphs are just kind of like graphs whose edges lie around a circle, right? Well, they don't have to be drawn this way. So this is one common way to draw cyclic graphs. I think their full characterization is just connected graphs such that the valence of every vertex is 2, right? Exactly 2. So these graphs can be drawn this way. So they are planar graphs. They all can be drawn in this manner, which means they're all planar graphs. And as such, right, since they all can be drawn this way, you can clearly see that for each of these graphs, they'll separate the plane into 2 faces, the one on the inside and the one on the outside, right? Okay, so then the face chromatic number, face chromatic number for cyclic graphs is 2, and this is always. Right, so every cyclic graph can kind of be represented in this way, right, where we're just kind of, you know, having vertices around a circle and then edges connecting them. And in that case, you know, we have 2 defined regions, the region on the inside of that circle that's formed, or that polygon, I should say, and then the region to the outside. So therefore, we only need 2 colors to color the graph, because these are adjacent faces, or adjacent regions, if you will. All right, and therefore the face chromatic number is just going to be 2. All right, so we're going to look at another family, right, rectangular networks, which we had already seen once before in this video. Okay, so rectangular networks. Okay, right, so we saw that the face color or face chromatic number of this particular rectangular network with 9 vertices in such a way is 3, right? So we can color the outside one color, these 2 separate colors, right? So 1, 2, 3, and then these 2 can be the same color since they're not adjacent, and these 2 can share the same color because they're not adjacent. So the face chromatic number of this graph is 3. Right, this rectangular network is 3, whereas for this rectangular network, it's 2, right? And for this one, it's going to be 3, because we have 3 faces that are simultaneously adjacent. For this one, it's going to be 3, still, because we can just color this the same one as that one. Right? And so if we add faces to one column, that does not change the face chromatic number, okay? Because we can just alternate which colors appear where. So in fact, we can actually, for any such rectangular network, kind of do this kind of checkerboard pattern, right? 1, 2, 2, 1, 1, 2, 2, 1. Okay? So this holds for any number of rows and columns. We can do this checkerboarding of the faces on the inside, right? Which means that we can use only 2 colors to color the faces on the inside of the rectangular network, and then we'll just need a 3rd color for the outside, right? So I'm kind of providing an informal argument as to why this is the case, but we have the general result that rectangular networks have face chromatic number equal to 3 if number of rows or calls is greater than 1. Okay, so if either the number of rows or columns of the rectangular network is greater than 1 strictly, we have that the face coloring number is going to be 3, right? Because we can do a checkerboarding on the inside and then have the outside with 2 colors and then have the outside be a separate color, right? The outside face have a separate color, right? But, you know, this graph is technically a rectangular network, so we can, you know, and this has a face coloring number, or face chromatic number, excuse me, of 2, right? Only need 1 color for the inside, 1 color for the outside face. All right. Okay, and then lastly, we'll talk about the family of wheel trees, which look like, you know, one of those old wagon wheels where we have kind of like a circle on the outside and then a spoke in the middle, and then we have, or I don't know if this is a spoke, an axle, and then spokes, you know, from the wheel, outside wheel to the middle here. So these are planar graphs, anything of the sort. So this one has 5 vertices, where we can do another with maybe 6. So these are all connected to the outside. Do the axle in the middle, and then, you know, there you go. Okay. And so each of these splits the plane into separate faces bounded by the edges, right? And we could see how many colors we'll need for, so there's also one with 4. So let's see what the face chromatic number is for the wheel graph with 4 vertices. So these are wheel graphs. So with 4 vertices, we can kind of color this face and this face the same color, these 2 faces the same color, and then the face on the outside the same color. So the face chromatic number, face chromatic number is 3 of that graph, right? Okay, so we had an even number of faces on the inside, right? What about when we have an odd number of faces on the outside? So for an even number of faces, this should always be the case, so we can make do with 2 colors on the inside, right? So because we can alternate evenly on the inside. Okay? Right? So because we can alternate evenly on the inside, we can make do with 2 colors for the faces on the inside of a wheel graph if there are an even number of wedges, right, on the inside. Right? So this would also have a face chromatic number of 3. So that holds whenever there are an even number of wedges on the inside, which means that the wheel graph has an odd number of, even number of faces on the inside, which means that the wheel graph would have an odd number of vertices in total, because you're at, you know, even on the outside, and then this one would make it odd. So what about the case when we have an odd number of wedges on the inside? So we'd need to do kind of 2 colors, 2 different colors, right? And then we'd need a 3rd color for the inside, and then since this outside face is adjacent to each of these, we'd need a separate color for that. So this would have a face chromatic number of 4, okay? All right, so we can maybe write a general result, which we're not going to prove, but it would say that the face chromatic number, this can be proven. It's not much work to make the argument that I've provided here more rigorous, but anyway, that's beyond the scope of this class. So the face chromatic number of a wheel graph it's going to be 3 if n is odd, and 4 if n is even, where n is number of vertices. Right, so remember that these wheel graphs that generate an even number of wedges on the inside have an odd number of vertices in total, right? So this is the result for the phase chromatic number of wheel graphs. So the regular structure and the predictable structure of each of these, or of graphs in these graph families, allows us to know what the phase chromatic number is without much effort. All right, so the possible values for the phase chromatic number are almost as limited as that of the edge chromatic number, at least for simple planar graphs. A famous theorem called the four-coloring theorem, proven in 1976 by mathematicians Kenneth Appel and Wolfgang Haken, states that for any such graph, simple and planar, its phase chromatic number will be no more than 4. So this result ties directly into a pertinent application of phase coloring, that is the coloring of maps. So we have that for any geographic map portioned into contiguous boundaries, right? For example, a map of the continental United States, we can color the entire map using only 4 colors, right? So that's what that result states. So the phase chromatic number can only be 1 through 4, okay? All right, so so we can use this result or apply this result to the situation when we're trying to color a geographic map. So how do we use this result? Well, we know that we only require 4 colors to color each kind of boundary, whether it be a territory or a county or a state, using only 4 colors. And so why is this important? Well, or why would we be interested in coloring a geographic map? Well, it would allow for easier distinction between its component counties, states, etc. Okay, all right, so that's the one application that we'll talk about. There are many more applications of phase coloring, but we're going to instead focus on an algorithm for finding a specific coloring for the remainder of this video. All right, so as in the case of the vertex and edge coloring problems, there's interest in finding a specific coloring that attains the phase chromatic number, meaning that it uses, as the number is specified by the phase chromatic number. So it uses there's a coloring, we're looking for a coloring that uses as few colors as possible, so a specific coloring. And as mentioned in those respective videos, this can be a difficult task, right? Just knowing how many colors would suffice for coloring a graph does not actually help us find the coloring. So again, there are certain graph families for which efficient algorithms are known, but we might, for generating such a coloring, but we might want something that can be applied in every situation. So regardless of what pattern the graph might have. So just a general algorithm. So since the coloring of components, right, either the edges, faces, or vertices is an incremental process, we can use a general backtracking algorithm to find a minimum coloring of a graph for which we know its relevant chromatic number. So I'm talking in generality here about this problem of finding a specific coloring, because it's essentially the same whether you're talking about coloring all of the vertices of the graph so that no adjacent vertices are the same color, or coloring all the edges of the graph so that no adjacent edges have the same color, or coloring all the faces of a graph so that no adjacent faces of the graph have the same color. It's kind of the same process of picking one of the edges or picking one of the vertices or picking one of the components, choosing a color, right, and then moving to the next component, seeing what colors are available, and choosing one of those colors. It's all that same kind of incremental process for each of these types of colorings. So this algorithm applies to each of those problems, right, of coloring either the edges, vertices, or the faces, right? And so here's the algorithm. It's a backtracking algorithm. So what you do is you make a list of the components to be colored, right? So make a list of all the vertices, or make a list of all the edges, or make a list of all the faces of the graph. And then for the first component in the list, we pick one of the possible colors with no preference. So you can do it at random maybe, right? Okay, so for the next component in the list, determine what possible colors it can be, and then choose one, again with no preference. And so then you repeat this step of choosing the next component in the list, looking at what colors are available, and then choosing one. And if at any point you run into a situation where considering a component in that list, and there are no possible colors it can be, what you do is then back up to the previous element and choose a different color from the colors that are available, right? And so this is the backtracking, and then in this, hence the name, backtracking algorithm, right? And then you just can repeat step 4 until the graph is colored. This constant choosing the next component, trying to color it. If there are no colors, go back to the previous element. Whereas if there are colors, choose one of those colors at random and then move on to the next component. And then you can do this until the graph is colored. So backtracking algorithms, if you have what are called partial solutions, meaning that you kind of, along the way, build up a solution that can be expanded upon, with incremental steps, then you can kind of use this procedure for that kind of problem. Right? So this algorithm is horrible performance-wise, and it provides nothing more than a systematic way for generating a coloring of a graph whose chromatic number we know. So you can kind of modify this algorithm for trying different numbers of colors, right? But then you're really talking about a poor performing algorithm at that point. So that does it for our discussion of the coloring problems. We're going to continue next week with a discussion of identification numbers, and that'll wrap up the class. I'll see you then. Bye.